This lesson is part 2 of section 10.2. Today we're going to continue to talk about the law of sines and the law of cosines. So we're going to use the law of sines and cosines in application problems, so we'll focus on that in the back part of our notes. And then we're also going to determine if there are one, two, or no triangles to a given problem. First, I just want to summarize when we use the law of sines and the law of cosines. Now, we use the law of sines and the law of cosines to solve oblique triangles, triangles that are not right triangles, because otherwise we would use Pythagorean theorem or SOHCAHTOA or other methods. Now, the law of sines is nice and easy to remember, so that's why students like it. And the law of cosines is not as easy. There's a lot more memorization, there's more calculations, but the law of sines doesn't always apply right away. Take, for example, this particular triangle where we're given 3 pieces of information, but the order is very important here. We have side and then an angle, the included angle, and then another side. We'd have to use the law of cosines first because we don't have a complete set to set up our proportions in the law of sines. We need at least an angle and the opposite side in order to solve for either a missing angle or another side. So in this case, we would use the law of cosines first to find this missing side length, and then we'd have a complete set of information. We'd have both a side length and its opposite angle, so we have a complete ratio. Then once we have that ratio, we can find the other angle here, either this angle or this angle, and to find the third angle after using the law of sines, we would then use the Triangle Sum Theorem, which just says that all 3 angles add up to 180. So you want to take shortcuts, obviously, where you can. You don't need to use the law of cosines every single time to solve, for other angle measures. You also don't need to use the law of sines to solve for that third angle. Now here's another example where the law of sines doesn't work right away, but what we could do very easily, we don't have to use the law of cosines here because all we need to do is find this angle measure here by subtracting all of these from 180, and then we have a complete ratio. We'll have the opposite angle and its side length, so we can set up the law of sines now to find our missing sides. Now notice here we're given 2 angles and the included side. So here's another straightforward use of the law of sines. You don't need the law of cosines here because we can find a third angle. We can also set up the complete ratio here since we have an opposite side length and its angle measure. And then we can obviously find the other missing sides. So far we haven't really had any problems using the law of sines. Now this might be taking you way back to some geometry from your freshman year, but remember when you were proving 2 triangles congruent, you had a few different methods that you could use. The method that you could not use, though, was angle side side, right? That did not have enough information to show that 2 triangles were congruent unless, of course, that angle was a right angle and then it became HL, hypotenuse leg, which is a special case of that word I can't say out loud. Now please don't panic and try to memorize each one of these cases here because that's not really the point of why I'm introducing it like this. Really, we only have to worry about one case, and that's going to be this case right here. But basically, the law of sines worked just fine in those examples that I showed you when you're dealing with angle, side angle, and angle, angle, side. Notice that you have 2 angles and then a side length. So it really doesn't matter where that side is as long as you have 2 angles and a side, law of sines works just fine. It even worked okay with side angle side, it's just that we had to use the law of cosines first and then we could apply the law of sines. I'm going to wait and talk about the side 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 case after we talk about this particular case, and we actually don't need to worry about HL at all because that's dealing with right triangles and we're solving oblique triangles. So let's come back now to our note sheet where we're going to discuss that special case, the ASS or SSA case. So if you're given 2 angles in one side, like we just talked about, angle, side angle, or angle, angle, side, the law of sines will provide you with just one solution for a missing side. However, the law of sines has a problem dealing with SSA, just like we can't use SSA to prove 2 triangles congruent. It doesn't guarantee a side length, so the law of sines is difficult to use. The law of sines could provide you with no solution, 1 solution, or possibly 2 solutions for an angle measure. Okay, now there's some background information before we even get started that I need to review. Now remember, the sine function has a range of -1 to 1. The inverse sine function has a domain of -1 to 1 and a range of -π/2 to π/2, which means your calculator will only give you values within this particular range. And finally, if the sine of theta is positive, then we know that theta has to lie in either the first or second quadrant, meaning we can draw this, depict this here. If the sine of theta is positive, then theta must fall somewhere on the unit circle here between the first and second quadrant. Alright, so we'll keep all of this information here, these facts, in mind now when we start solving these particular angle side side problems. All right, in this first problem, it says that in triangle ABC, little a is 20, little c is 16, and big A is 30 degrees. We're supposed to solve the triangle. That means we need to know at least one side length, because we're given 2, so we need one more side length. And we also need 2 more angle measures. We're going to need angle B, and we're also going to need angle C. So that's what it means to solve the triangle. We need all 6 parts. So I'm going to draw a preliminary sketch here of triangle ABC. Now I'm calling it a preliminary sketch because I don't know which sides are biggest. I don't know which angles are biggest. So this is kind of the best I can do. It's just a really rough sketch. So opposite this angle A, which is 30 degrees, I have a side length of 20. And opposite big C here, I have a side length of 16. Now as you can see, the order here is angle, side, side. So this is definitely a case of angle, side, side. So, based on what I've drawn, it looks as though the law of sines definitely applies here. I have one complete set of information here, so I can say the sine of 30 degrees over 20 is equal to the sine of C, big C, over little c, 16. And if I solve here to isolate angle C, I have the sine of C is equal to 16 times the sine of 30 degrees over 20. Now I can evaluate the sine of 30 degrees. The sine of 30 degrees, that's the closest to the x-axis, so that'll be 1/2. So I have the sine of C equals 16 times 1/2, so 8 over 20. Now that ratio is 4/10. So I can plug that in, or 2/5. I can plug that into my calculator now. So if I have the sine of C is equal to 2/5, let's take the inverse sine of 2/5 to isolate C. All right, so we take on our calculator and we type in the inverse sine of 0.4 2/5 here. We end up with 23.57 degrees. Now this is where we have to remember our limitations of using our calculator to solve for theta. Because remember, the sine of C is equal to 2/5. It's positive, which means that it could lie anywhere between the first and second quadrant. So C is somewhere in the first or second quadrant. Our calculator, though, is limited to only giving us values, right? Its range, the inverse sine function's range, is only from negative pi over 2 to pi over 2. So even though it's giving us this particular solution here, there is another one on the other side that we need to get. So what we'll have to do now is take 180 minus that angle 23.57. Whoops, I definitely didn't do that. All right, so anyhow, we get 156-ish. Okay, so we have 156.4. Now, if we have 2 angle measures, so right now we're saying angle C can either equal 23.57 or 156 point, I forget, but whatever. Okay, so here are 2 angle measures. Now, think about the fact that if you plugged in angle C as 156, clearly that's already over 180 degrees. That will not work. This is not a valid angle measure. This one is your angle measure then. So to solve now for the rest of the picture, you can subtract from 180 to find this missing side length, or I'm sorry, this missing angle, and then find your other missing side just using the law of sines one more time. So we would take 180 minus 30, minus this is now 23.57. So let me fill that in. Okay, and then find that angle. And again, once you have that angle, I'm not going to do this whole problem because I think after this it becomes pretty easy how to solve for this measure here. Now you can set up law of sines because you have this ratio. You have one part here and you can use any of the other 2 ratios. I would use the sine of 30 though, as opposed to this rounded value. Okay, so this is a case where you end up with one solution. Okay, we started off with 2 possible theta values, but only one actually works within the triangle. We have to consider both though. Always make sure you're considering both. This 156 does not provide you with a valid triangle because you could not have, angle measures that are over 180 degrees. So now that's one type of angle side case. Now there's another. Okay, if you have a setup like this, so we do it very similarly. Okay, we have a sine of angle A. Angle A is 30 degrees, little a is 7. Let's make big C here, and little c, is going to be 16 then. And here we've got angle B. All right, now to set up, in this case, we can again use the law of sines. Here I've got the sine of 30 over 7, so that's a complete ratio. So the sine of 30 over 7 should equal the sine of C over 16. So again, I just want to reiterate that we're doing angle, side, side. So we're given an angle and then side, side. All right, now to solve for c here, very similarly, we have the sine of c is equal to 16 times the sine of 30 over 7. Now if we simplify here, we have 16 times. The sine of 30 is going to be 1/2 again, over 7. Well here, 16 times 1/2 is 8/7. So 16 times 1/2 is 8, divided by 7 gives me 8/7. Right away, even before you type this in your calculator, I'd like you to realize, hey, that value is over 1. We can't have, the sine of c can never be over 1. Its range is only -1 to 1. So that means that the inverse sine is trying to calculate something that cannot possibly exist. Whoops. So the inverse sine of 8/7. That is not within the domain of the inverse sine function. So you'll see that actually when you try to calculate this. It's the inverse sine of 8/7. You will get this error message here. It says domain. So you're not able to answer or to enter that within the inverse sine function. So here is a case where there is no triangle. Okay, there is no such triangle that would have these particular side lengths in this particular angle measure. So here we get no solution. Okay, we can't solve this triangle because it cannot possibly exist. Now the third type of case with the angle side side, we call this the ambiguous case. All right. So we have a triangle here, similar setup. We still have angle side side. I have angle A is 30 degrees, opposite angle A is 10. Opposite big B here is 16, and I've got big C. All right. Now if I set up the sine of 30 over 10, this starts looking totally normal still. I've got sine of 30 over 10 is equal to the sine of B over 16. Now if I want to solve for b, I have the sine of b is equal to 16 times the sine of 30 over 10. So here I have the sine of b is equal to, again, 16 times 1/2 is 8, so 8/10. So if I want to solve for b, I need to take the inverse sine of 8/10. So I can type that right into my calculator now. So inverse sine of 0.8 here. And this time I get 53.13. Okay, and again, sine is positive in the first or second quadrant. Our calculator, though, will only give me solutions between -pi/2 and pi/2, so, or negative 90 degrees and positive 90 degrees. So right now I have this possible angle measure, 53 point, I've already forgot it, 0.13. All right, we have an alternative value over here on the other side of that unit circle. So I need to take 180 minus 53.13 to figure out what that value is. So some of you guys, I think, have a hard time with this whole reference angle thing. Just think of it in terms of arc length even. So that arc length here needs to be the same as this arc length over here. So if you want to find this value, I'm using a lot of colors here, but if you want to find that value, you just need to take 180 degrees and subtract that arc length here, which is the measure of the, I guess you should say arc measure, I'm using the wrong vocabulary term, but that will leave you then with this entire angle measure here, okay? So we take 180 minus 53.13, and I just like to be really exact. You either need to store your values, I didn't really talk about that much yet, but you need to store your values, and I'll show you how to do that in just a second, but I like to take 180 minus the answer, so I never clear out that answer, I never round it, because I want to get as you know, close to the exact as I can. So we get 126.89. So we have two possible values for B. Right now we have 53.13, but B can also be 126 I guess 86 or 87 here in this case, since I rounded to the nearest tenth there. So those definitely add up to 180 there. Okay. Now this time when I try to test whether or not these make sense within the original triangle, this time this obviously works because that's still going to be less than 180 degrees when I add 30. But here when I take 126.87, that's actually okay to try to use 126.87. This value here is still less than 180 if I try to add up the angles of this triangle. So that means that I can just use Triangle Sum Theorem to find angle C. So this is giving you two possible triangles. This is why it's called the ambiguous case. Ambiguous means to be up for interpretation. So multiple interpretations. Well, here's our multiple interpretation. We can have a triangle that has an angle measure here at angle B of 126.87, or we could draw another triangle So here our side lengths would be fixed, but this angle measure here is 53.13. And this is just basically showing you why angle side-side never works, because it doesn't guarantee triangle congruence. These two triangles are clearly not congruent. And once I solve for that other angle measure here, I get a completely different side length here. X and Y would be totally two different values. So in case you're very confused at why there are two unique triangles created when you're given angle side-side, I found this online applet that I think does a really good job of visually demonstrating the ambiguous case of the law of sines. So here, for some reason my cursor is not showing up for you guys, but I'm hovering around angle A right now. Angle A is a fixed angle, okay? This is an angle that's given to you. So it's not changing at all in this applet. Side AB is also a fixed length. Then we have BC, okay? The length of BC is also a fixed length, but as you can see, you can swing that, create a new angle, and you still have a triangle with the same angle measure, the same fixed side length, and BC is also fixed. All right, so I just took a screenshot, so unfortunately we kind of lost the interactive part where it's moving, but we've got that fixed angle here. We've got a side length that is also fixed, and we have this other side. So we can swing this angle and create a completely unique triangle now that still has the same exact angle measure for angle A, the same length for AB, as well as the same length here, the BC here now. Obviously we're relabeling and calling it BD. So we've got two unique triangles here. Okay, let me highlight one of them. So here's triangle ABC. And as you can see, this angle measure here is obtuse. We also can create triangle, let's do this one, triangle ABD. I didn't go in the same order, but this angle here is acute. Okay. Now that's exactly what we saw here when we were solving for B. We had two possible angle measures. The obtuse one still worked. It still, when we added it to the original 30-degree angle, it still created a possible triangle. So obviously when I ask you to solve this triangle, you need to give two pictures. You need to show both of these possible triangles. So you're going to solve then for angle C. So you would subtract, find angle C, and then find side length Y here, which I labeled Y. Or I guess I should have labeled it little c. But you should find little c here by using the law of sines. Okay? Now, the same thing applies for this other triangle, so you would just fill in these parts. I'm not going to do that with you because I think that's a pretty easy task from here. So now we're going to move on to that other case, that side case. Here we're given three sides of our triangle. You might recognize this problem because I did this yesterday in the notes, and I used the law of cosines here obviously because I can't use the law of sines. It doesn't apply here since I don't have a complete ratio. Now when I worked out this problem, I kind of went the slow way. I first worked out angles B and A. I don't remember the order, but I did B and A first, and then I subtracted from 180 to get angle C. I did the law of cosines for both of those angles, even though that was a tedious calculation. Now today I'm going to show you a little bit of a shortcut on this kind of problem. So we still need to use the law of cosines first. Obviously, again, because you can't use the law of sines. However, this is a very important step here. You're going to solve for the largest angle. Now the reason we solve for the largest angle is really abstract, and it relates back to the range of your inverse cosine function and your inverse sine function. Now our inverse cosine function has a range of 0 to pi, while our inverse sine function, I know I've said this a bunch of times already, has a range of negative pi over 2 to pi over 2. So when I use my calculator and I'm using the law of cosines, I must use the inverse cosine function if I'm solving for an angle. So at some point I'm going to have to hit on my calculator inverse cosine of, let's say it's a crazy ratio where we don't have the value memorized. Well, that output, that theta value, will be between 0 and pi, meaning I can get an acute angle, which would be represented between here 0 and 90, or I could get an obtuse angle between 90 and 100. Whereas if I ever try to solve for the largest angle using the law of sines, I'm only going to get values between negative pi over 2 and pi over 2. Now in our calculator, those values, since our sine ratio is positive, will always be here as opposed to over here. So we could possibly have a triangle where we want this particular value, but our inverse sine function, our calculator, will only give us this one. So that's why here we start with the inverse cosine function, solve for your largest angle. By solving for your largest angle, you can get already an obtuse angle, whereas here you can't in the inverse sine function. But then you guarantee, so the fact that it's the largest angle will guarantee now that the other remaining angles must be acute, right? You can't have more than one obtuse angle in a triangle. And even if this angle is acute here, since it's the biggest, the other two must be smaller than that and also acute, all right? So after you use the law of cosines to find the largest, then you can, of course, use the law of sines. So LOS. Use the law of sines next. Because it is faster than using the law of cosines, and it's an easier calculation. So I'll let you guys try that one on your own and then check with the key. All right, you're an avid bird watcher, because what 17-year-old high schooler is not? Okay, you spot the highly coveted yellow-headed blackbird in a tree north of where you are standing. You have an excellent eye for angles, and so from your current spot, you realize the angle of elevation is 34 degrees. You walk about 20 feet closer to get a better look, and your angle of elevation is now 43 degrees. There are two questions here. How far are you from the bird, and how high is the bird's nest? The most important part of doing this problem is making sure your diagram is correct. So there are a couple of things here which I think could maybe mess you up a little bit. First of all, it says you are spotting a bird north of where you're standing. So people will make a spot for where they're at and then try to draw in the bird directly above. Now, the fact that it's north of where you're standing doesn't mean that it has to be directly above. You could be facing north, and north could be this direction here, right? And then I would be able to draw a bird way up here in a tree. So really, I'm looking at a horizontal line, which represents the ground, and a vertical line, which represents the tree. So look at my beautiful tree. Okay, I spot the bird. I'm at a spot here, looking up at the bird, at an angle of elevation of 34 degrees. I walk about 20 feet closer, so now I'm a little bit closer. This angle now of elevation here is 43 degrees. So I want to make sure I'm accurately drawing this. I've got a 20 foot segment here, and this is definitely a right triangle. Now these two triangles are not similar to each other. Clearly they are not similar to each other, but I want to solve for two different lengths. It says, how far are you from the bird? The distance between myself, which is here now, and the bird is represented by this segment here. So I'm going to label that X. Now I also want to ask how, or answer how high the bird's nest is as well. So that will be this segment over here. Let's label that Y. We should focus though on only solving for one of these segments first. So if you want to pause the video, you're more than welcome to. Check with the key, and if you don't get it right, then make sure you come back and watch the whole explanation. The reason why I picked this problem is because I think it's easy for somebody to get stuck trying to solve. Anyhow, let's focus now on solving for X. So if I want to solve for X, I'm going to isolate that triangle here, and I'm just going to look inside here to see what I can do. So I've got X, 34 degrees, and this is 20. Now, if I try to use the law of sines, I don't have quite enough information yet because even though I have, X over the sine of 34, I don't have this angle measure up here to use the ratio there. So I'm kind of missing a little bit of information. Now, I would have that angle measure if right away I had tried to fill in as much of information in the diagram as possible. See all these angle measures that are missing here? I would definitely go through and just write them in, fill them in. For example, here, you know that this angle measure has to be 137 degrees. So I'm going to label that as 137 degrees. I can also solve for this angle here using 180 minus 43 minus 90. And then after I get that angle measure, I can do the same thing again using 34 degrees here, and this whole measure, and the 90 degrees. So I end up with 47 degrees here, and that would make that 9 degrees, I believe. Okay. Now I'm okay to set up, since that's 9 degrees here, this little angle measure, now I'm okay to set up the law of sines. So I have the law of sines, which states the sine of 9 degrees over 20 is equal to the sine of 34 degrees over x. And actually, it probably would have been easier if I had set it up with x on top. That kind of a silly thing for me to have done and put it in the denominator. But oh well. So solving for x, we end up with 20 times the sine of 34 degrees over the sine of 90 degrees. Or I'm sorry, that's just a 9. So that's my exact answer. Now when I type that into my calculator, I want to make sure that, one, you know how to type it in, but also that it's in the right mode and that I can store that value. So here I've typed it into my calculator already, and I end up with 71.49 feet. So that's the distance between where you're at right now currently and where the bird is at. So 71.49 feet. So that's an approximate value. We want to make sure that you're carrying the correct value, which is the exact value, throughout your equation. So rather than having to type that in every single time, you can simply store that value. So I'm going to hit stow, and that's ghetto for store, so it's that button right above the on button, and then hit alpha, either A, B, C, anything. You can save it as X though. I just keep it consistent because I labeled it X in my diagram. Just label it X here. You can use that X button here up top as well. Alright, so I hit enter, and now that value is stored. Now when I solve for y, that's going to be much more straightforward. Solving for y here, I have the opposite, and I already know this side length here, that's the hypotenuse, so I can simply use the sine of 43 degrees or even the cosine if I wanted to of 47. So I'm going to set up the sine of 43 degrees is equal to y over x. So to get y by itself, now I have it in terms of x, but I know what x is, so that'll be a quick calculation that I just type right into my calculator. So I have y equals x times the sine of 43 degrees. So inside here I can type in x, so alpha x times the sine of 43, and I end up with 48.57, or 75, sorry. So 48.57, I think I just transposed them again. Oh, yep, 7.5. Okay. So this is the approximate value. Whoops, should have an approximate symbol there. For the height of the tree, or I should say not the height of the tree necessarily, but where the bird's nest is in the tree. So that's 48.7 feet off the ground. If you don't store your values, these decimal places will be off by a significant portion after you keep, using problems or using these numbers in the problem. So make sure you don't create a large margin of error. Always store your values. Now question 6 is going to be a review question of some geometry that you did your freshman year actually. We want to find the perimeter and area of a pentagon that is inscribed inside of a circle. So we talked a little bit about this already, but if it's got a radius of 7, that's this segment here. And that is going to give me a triangle. So it's an isosceles triangle. Both of these segments here are 7. Now, the one thing I'm missing here in order to find the perimeter and area is this angle measure theta. Okay, to find that, remember we take 360. Since it's a regular shape, that means all of these chords are the same size, which means the arc lengths and the arc measures are all congruent. So that arc measure here, in this case, if we divide by 5, we end up with 72 degrees. So we now have a triangle, an isosceles triangle, that looks like this. And to solve for this segment here, which will help us get the perimeter, remember if these segments are all the same, I just find this length here and multiply it by 5 to find the total perimeter of the pentagon. Now to find that segment, that's simply a law of, cosines question. So we would find it using the law of cosines. So we have a bit of a calculation here, but not too bad. So for perimeter, make sure you're multiplying the x value here by 5 to find the full perimeter. Now when you're finding the area of this circle, I think you could do it a couple different ways, but you can do again 1/2. So area is 1/2 AB sine theta. Remember our formula, and AB is just the included, the two segments where the included angle is given. So here I've got the two segments here, side angle side. So that's the included angle between them. So I would just take 1/2 the product of 7 and 7 times the sine of 72 degrees. Again, that's the area of just one triangle. To find the area of the pentagon, I need to multiply that all by 5. So that's using our method of what we just learned. However, you can do this problem using the same stuff that you guys used in geometry, where you used Pythagorean theorem and right triangle trig. So let's talk about this isosceles triangle. Since we know it's isosceles, I can actually split this up here. If I create that altitude, that's going to split this up into two congruent triangles. Now that 72 degree angle becomes 36 degrees. And now to solve for this opposite side here, I would just use the opposite over hypotenuse. So I use the sine of 36 equals, let's call that, I guess we could call it x over 2. I don't really want to. Let's call it a new variable a. So a over 7 So 7 times the sine of 36 equals that segment. Well, then I have to double it to find, the full length of x, and then I multiply by 5 to find the perimeter. Now, if I want to find the area of this triangle, I have to find the base and the height using our normal, base times height. Let's say we forgot this formula here. Okay, so let's use base times height. We have our a value. Let's find our height. Now this segment, let's call that b. That's the adjacent side. This is the adjacent side, and I have my hypotenuse, so I'm going to use the cosine. So the cosine of 36 is equal to b over 7, which means b is equal to 7 times the cosine of 36 degrees. So hopefully you're following, because I know this is a lot of work. I'm going to erase a little bit here. Okay, now if I want to find the area of this triangle, this little triangle here, I would take 1/2 times the base, 7 times the sine of 36, times the height, 7 times the cosine of 36. So that's the little triangle. Now to find the big triangle, since they are the same size, I would double that. Okay, so now those cancel. That leaves me with 7 squared times the sine of 36 times the cosine of 36. See how related that actually is to this answer here, where we have the area of this triangle? We have the sine of 72 degrees. Think of that as 2 theta. So you have the sine of 2 theta here. And if I use my angle identity, I end up with the sine 2 times the sine of theta times the cosine of theta, right? Well, here's sine of theta times the cosine of theta. And the 2 has been divided out here, and that's why you have that 1/2 here. So I think that's pretty cool. You see it both ways using an identity even, but you can do it still with right triangle trig, or you can use our new formula, which requires you not to know the height. Wait, did I just say that right? The new formula doesn't make you know the height of the triangle. I still don't think I said that right. Okay. Anyways, let's move on now to number 7. Number 7 says find the area of a triangle with side lengths 3, 6, and 7. So we draw our triangle here, and you don't have to be an excellent artist. Just try to make it oblique if you can, since it's definitely not a right triangle. And then just label it as so. Okay, so we have 3 different side lengths. This is similar to the question that we had, number 4 on the top of our page. But basically, we want to find the area. Now, I don't need to know the height of this triangle if I use 1/2 AB sine theta. That's why this formula is kind of nice. You don't need to know the height. So let's find an angle measure that's worth finding, and that's always going to be your largest one. So I want to find this particular angle value because it's opposite the largest side. Then I would use the 6 and the 3 as the included sides here, so that I could take the sine of whatever theta is. So A and B are 6 and 3, and then find the area. I would like you guys to try that one and check the key as well. I'm trying to keep this video short. Nice job. I will see you guys in class tomorrow.